In January 2024, the James Webb Space Telescope locked onto a neutron star sitting 6,500 light-years away and detected something no one had predicted. A moving object, circling the corpse of a dead star. In a region where nothing, by any physics we currently understand, should have survived. The team ran the numbers 3 times. The results didn't change. And the explanations they came up with, the serious, peer-reviewed, published in respectable journals explanations, are somehow more unsettling than the mystery itself. And I keep saying dead star, but that's actually part of the problem here. Because neutron stars aren't really dead. There's something far stranger than dead. We'll get into that. But first, I want you to understand why this particular signal, from this particular system, sent shockwaves through the astronomical community in a way that most space news simply doesn't. By the time we reach the end of this documentary, you'll understand exactly why this discovery is being called the most disorienting find of the Webb telescope's operational career, and why the answer, whichever answer turns out to be correct, says something profound not just about the universe, but about us. About what we are, where we fit, and whether the question we've been asking, are we alone, has been framed correctly all along. There are 3 leading theories about what this object is. The first one is strange but has precedent. The second one challenges our entire model of how planets form. And the third one is the reason this story has moved beyond astronomy departments and into conversations that some scientists would rather not have in public. We're going to walk through all of them. Carefully. Honestly. Without pretending the uncertainty isn't there. Let's start at the beginning. With what a neutron star actually is, and why finding anything near one should be, by every measure we have, impossible. Imagine the most violent event the universe is capable of producing. A star, something between 8 and 20 times the mass of our Sun, has spent millions of years burning through its nuclear fuel. When that fuel runs out, the core collapses. Not slowly. Not gradually. In less than a second, the core goes from the size of Earth to the size of a city. The outer layers fall inward, hit the newly collapsed core, and bounce back outward in an explosion that releases more energy than our Sun will emit across its entire 10 billion-year lifetime, released in a matter of seconds. That explosion is a supernova. And what's left behind, sitting in the center of the expanding debris cloud, is a neutron star. The numbers here are genuinely hard to hold in your head. A neutron star is typically about 20 kilometers across, roughly the width of a mid-sized city. But its mass is between 1.5 and 2 times the mass of our Sun. Every teaspoon of neutron star material weighs approximately 1 billion tons. The surface temperature runs around 1 million degrees Celsius. Compare that to our Sun's surface at roughly 5,500 degrees, and you begin to get a sense of the scale we're operating at. And then there's the magnetic field. We'll come back to that. Now, given everything I just described, the explosion that formed it, the radiation it continuously emits, the gravitational and magnetic forces operating at scales that simply don't have everyday analogies, what are the odds that anything survives near a neutron star? That anything remains in orbit, intact, after the supernova that created it? The answer, according to the models we had before January 2024, was vanishingly small. Not zero, but close enough that finding such an object would qualify as a genuine anomaly worthy of serious attention. Here's where history adds something important. In 1992, a Polish astronomer named Alexander Wolzin was analyzing timing data from a pulsar, a rapidly rotating neutron star that sweeps a beam of radio waves across space like a cosmic lighthouse. He noticed something odd. The timing of the pulses wasn't perfectly regular. There was a wobble, a pattern. And that pattern was consistent with not one but 3 planetary bodies orbiting the pulsar, pulling it very slightly toward and away from us as they orbit it. His discovery, confirmed and published that year, was the first confirmed detection of planets outside our solar system. Not around a sun-like star. Around a dead one. And here's something that always gets me about that story. Wolfson's pulsar planets were the first confirmed exoplanets ever found, and they were orbiting something that should have destroyed them. So in a way, the entire history of exoplanet science begins with an anomaly that didn't fit the model. It begins, specifically, with someone who didn't dismiss a weird signal. But here's the critical difference between what Wolfson found in 1992 and what Webb detected in early 2024. Those 3 pulsar planets had stable, predictable, mathematically clean orbits. They moved exactly the way objects under gravitational influence should move. The object Webb detected does not. Its motion pattern, the acceleration and deceleration, the trajectory, doesn't fit any known orbital category. When the team at the Space Telescope Science Institute ran the motion data through their orbital mechanics models, the software flagged an error. Not an anomaly warning. An actual processing error. The object's trajectory doesn't correspond to any classified orbital type in the existing database. And that's where things get genuinely unsettling. So how did Webb find this? The telescope didn't look at this system and see an object the way you'd see a planet through a traditional telescope. The detection is more subtle than that, and understanding how it works is important, because the method is part of why scientists take the results seriously. Think about this analogy. Imagine someone is spinning a flashlight in a completely dark room, sweeping it at perfectly regular intervals, every 1.39 milliseconds, let's say. The flashes are so regular you could set an atomic clock by them. Now imagine something invisible is gently, rhythmically pulling on their arm. The flashes would come fractionally faster when that something pulls them toward you, fractionally slower when it pulls them away. The pattern of that variation, faster, slower, would tell you something is there, something with mass, something in motion around the person holding the flashlight, even though you can't see it directly. This is pulsar timing, and it's one of the most precise measurement techniques in all of observational science. Webb observed this system using its NIRISS and NIR-SPEC instruments, which operate in the near-infrared range and have spectroscopic resolution approximately 100 times finer than what Hubble could achieve in comparable observations. The telescope stared at this system for extended continuous periods, the kind of sustained observation that washes out instrument noise and background interference until what remains is a clean, robust signal. That signal was then cross-referenced against ground-based radio telescope data to rule out local calibration issues. What the data showed was a timing variation, a Doppler-like wobble in the pulsar's emission pattern, consistent with a companion object of at least 0.3 Earth masses. Not a grain of dust. Not a small asteroid. Something with the gravitational heft of a substantial planetary body, in a region of space where substantial planetary bodies have no business existing. And then there's the acceleration data. This is the part that moves the story from interesting anomaly to we need to talk about this carefully. A surviving planet, or a newly formed second-generation body, moving under gravity alone should follow a trajectory that obeys Kepler's laws. It should speed up as it moves closer to the neutron star, slow down as it moves away, the same elegant mathematics that governs every planet in our solar system. This object does the opposite in certain parts of its path. It accelerates when moving away. It decelerates when moving toward. Standard gravitational mechanics, applied straightforwardly, produces the wrong answer for this object's behavior. The team identified 3 potential natural explanations and found that none of them fully account for all the data simultaneously. I want to be honest with you here, and this is something science communicators don't say often enough. Some of what I'm about to describe lives in the space between confirmed data and theoretical interpretation. The detection is real. The motion is real. The explanations, those are still being argued over in peer review. And I think that's actually the most exciting part of the whole story. There are currently 3 competing theories. The first is strange but workable. The second challenges our model of planetary formation entirely. And the third one is the reason this story has spread beyond the astronomy community. Each one is stranger than the last. Theory 1 says this object is a survivor. It was there before the supernova, it lived through the explosion, and it's still orbiting what used to be its star. This isn't as far-fetched as it initially sounds, because we have precedent. Wolzin's 1992 planets are the proof of concept. Planetary bodies can exist around neutron stars. The question is how they got there, and whether survival or formation after the fact is the more likely pathway. The survival scenario works like this. Before the star exploded, it had a planetary system, perhaps not unlike our own. When the supernova occurred, planets at sufficient distance from the blast could theoretically survive the initial shockwave, stripped of atmosphere and reshaped, but structurally intact. According to planetary dynamics research from the University of Warwick group working on post-supernova orbital mechanics, if a planet was situated beyond roughly 5 astronomical units, 5 times the Earth-Sun distance, at the moment of the explosion, there's approximately an 8% probability of partial structural survival, based on modeling published around 2019 by Veris and colleagues. 8% isn't zero. But the story doesn't end with surviving the blast. After the supernova, the neutron star retains only about 40% of the original star's mass, the rest was ejected in the explosion. Less mass means less gravity. A planet that was bound to the original star by a certain gravitational force suddenly finds that force dramatically reduced. In most cases, it simply flies off, unbound, lost to interstellar space. For a planet to remain in orbit, or to be recaptured, requires a very specific set of circumstances that make the probability drop considerably further. Now picture what that survivor planet would look like. Every trace of atmosphere, scoured away. Any surface liquid, gone within the first million years, vaporized by the radiation environment. The surface, bombarded continuously by X-rays and relativistic particles from the neutron star, would be bare rock. Dark. No reflected light we could easily detect. A world reduced to its skeleton, circling the remains of its star in perpetual irradiated darkness. There's something about that image I find myself returning to whenever I think about this story. Billions of years of ordinary existence, a planet with weather, perhaps oceans, perhaps complex chemistry, orbiting a normal star. Then, in a few seconds, everything changes. The sky goes white. The atmosphere is stripped. The oceans, if they existed, boil away into space. And the rock survives, floating in the dark, in tight circles around whatever is left. It might be the loneliest image I can construct. But here's the problem with Theory 1. The motion data doesn't fit it. A survivor planet in a decaying orbit, and the orbit would be decaying, gradually spiraling inward due to tidal forces, should follow a trajectory we can predict. The acceleration-deceleration asymmetry we observe doesn't match that trajectory. It's not decaying. It's doing something else. Which is why a second group of researchers looked at the same data and reached a very different conclusion. Theory 2 doesn't just explain a different origin story. It proposes something that rewrites what we think planets can be made of. Theory 2 says this object wasn't there before the supernova. It didn't survive the explosion. It was born from it. When a massive star explodes, not all of the ejected material escapes the system. Some fraction of it falls back toward the newly formed neutron star, pulled in by gravity, and forms what's called a fallback disk, a swirling ring of post-explosion debris orbiting the stellar remnant. We've observed these disks. The supernova remnant SN 1987A showed debris disk structure. The pulsar 4U0142+61 had a confirmed fallback disk detected by the Spitzer Space Telescope in 2006. These disks are real. They exist. Here's the part that broke my brain when I first read about it. Under normal circumstances, planet formation takes tens of millions of years. Rocky planets in our solar system took somewhere between 10 and 100 million years to fully accrete from the protoplanetary disk. But a fallback disk around a neutron star is not a normal protoplanetary disk. It's far denser, far more compact, operating under extreme gravitational and magnetic conditions. Theoretical models suggest that planetesimals, the building blocks of planets, could condense from this material in thousands of years rather than millions. Not planet formation on geological timescales. Planet formation at fast forward. And the composition of what forms would be unlike anything in our catalog of known worlds. Normal planets form from the dust and gas that drifted around a star during its lifetime: silicon, iron, carbon, oxygen, water, ice. The material in a fallback disk was processed through the heart of a supernova explosion. It's rich in what astrophysicists call R-process elements, rapid neutron capture products. Barium, strontium, platinum, gold, radioactive isotopes. The gold in a wedding ring was forged in a neutron star merger or a supernova. That's confirmed science. Theory 2 is saying that there might be entire worlds, entire planetary bodies, made almost entirely of this material. A planet where the ground itself is composed of what we consider precious metals. I have no idea why that image isn't in every science textbook, but here we are. Webb's infrared spectrum of the object supports Theory 2 more than Theory 1. The spectroscopic signature is inconsistent with standard rocky planet composition and far more consistent with heavy element-enriched material of the kind you'd expect from supernova fallback. This is one of the strongest data points in the entire dataset. The motion anomaly also becomes slightly more explicable under Theory 2. A second-generation planet formed from fallback disk material would be geologically very young in orbital terms, still settling into whatever equilibrium its environment allows. Crucially, it would be subject not just to gravity but to pulsar wind pressure, the continuous stream of relativistic particles flowing outward from the neutron star's poles. That pressure, applied asymmetrically depending on orbital position, could produce non-standard acceleration patterns. It doesn't fully solve the problem, the numbers don't fit cleanly, but it moves the needle further than Theory 1. And then there's the implication that extends far beyond this one system. If second-generation planets form regularly after supernova events, and if fallback disks are a common feature of neutron star formation, which the evidence suggests they are, then our census of planetary bodies in the Milky Way has been systematically incomplete. There are roughly 100 million neutron stars estimated in our galaxy. If even a small fraction harbor post-supernova companions that we've never been able to detect before Webb, the number of worlds in the universe just increased in a category we didn't know existed. We've been missing an entire class of planets. But Theory 2, compelling as it is, still doesn't account for all of the motion data. The acceleration pattern has a directionality that pulsar wind pressure alone cannot explain. And that gap, that specific, stubborn gap in the physics, is where Theory 3 enters the conversation. Theory 3 was not published in a standard astrophysics journal in the way a completed, peer-reviewed paper would be. It appeared first as a preprint on AR14, the platform where researchers post work they believe in but aren't yet ready to submit for formal review, often because they know the community needs time to catch up to what they're proposing. When I tell you what it suggests, I want you to notice your own reaction. The researchers who wrote it anticipated that reaction and built their argument specifically to address it. The acceleration anomaly, object moving faster when receding, slower when approaching, in a pattern inconsistent with gravity and inconsistent with radiation pressure, has a very short list of physical causes. Asymmetric outgassing can produce non-gravitational thrust, the way a comet jets material into space and gets pushed by the reaction. But the object's mass estimate is too large for that mechanism to account for the observed acceleration magnitude. Magnetic coupling between the object and the neutron star's field could theoretically produce anomalous forces, but the directional consistency of the pattern doesn't match magnetic coupling dynamics. What does match, mathematically, in terms of the direction and timing of the anomalies, is the signature of active trajectory adjustment. Something that changes its own velocity independent of gravitational and radiative forces. Before I say the next sentence, let me give you the scientific framing. NASA's official definition of a technosignature is any measurable property or effect that provides scientific evidence of past or present technology. The key word is measurable. It doesn't require a radio signal. It doesn't require a communication beam. It requires a physical signature that, after exhausting natural explanations, is more consistent with technological origin than with any known natural process. By that definition, which is NASA's definition, not a fringe definition, an anomalous acceleration pattern without identifiable natural cause is a technosignature candidate. That's methodology. That's how the process works. The preprint's argument is precise. It does not claim this object is engineered. It claims that after accounting for all known natural mechanisms, the technosignature hypothesis cannot be ruled out with current data. In formal scientific language, cannot rule out is not a weak statement. It means the hypothesis is still alive. It's still in the race. This connects to a broader context worth taking seriously. In 2017, an interstellar object called Oumuamua passed through our solar system, the first confirmed interstellar visitor we'd ever detected. Its acceleration was anomalous. It was tumbling in a way inconsistent with comet outgassing. Avi Loeb, the former chair of Harvard's astronomy department, proposed that the light pressure hypothesis, that Oumuamua could be an artificially thin sail-like object, deserved investigation. The community largely dismissed it. But here's the thing, the anomaly was never explained. To this day, Oumuamua's acceleration doesn't have a clean, agreed-upon natural explanation. The dismissal happened without a replacement theory that actually fits all the data. Loeb subsequently founded the Galileo Project, a funded, legitimate research initiative specifically designed to apply rigorous scientific methodology to anomalous astronomical objects. The funding level was $1.7 million. This is not fringe science. This is institutional science responding to persistent gaps in our explanatory models. And here's the historical point that I keep coming back to. In 1967, Jocelyn Bell, then a graduate student, detected a radio signal of extraordinary regularity, pulses coming every 1.3 seconds with precision that seemed impossible for a natural source. Her research team initially labeled it LGM-1, Little Green Men 1, because it was too regular. too structured, too unlike anything they knew nature could produce. It turned out to be the first pulsar ever observed. The lesson cuts both ways. Natural phenomena sometimes look artificial. But the reason the LGM label stuck for a moment was because regularity without a known natural cause is a legitimate reason to ask the question, even if the answer turns out to be physics. I want to tell you something honest about my own process here. When I first read the AR-14 preprint, my reflex was to dismiss it. Years of consuming science content have trained me to be allergic to anything adjacent to the word alien. But then I went back and read it slowly. And I realized my instinct wasn't scientific, it was social. I didn't want to be associated with a conclusion that might make me look credulous. So I'm being deliberate now. I'm saying the scientific statement, which is that we cannot rule this out with current data. That's not the same as saying it's true. It means the question is still open. And I think, maybe, is the most scientifically honest word available to us right now. Whatever this object is, survivor, second-generation world, or something else entirely, it persists inside one of the most hostile physical environments in the known universe. And understanding just how hostile that environment is changes what survival means here. A neutron star's magnetic field runs at approximately 10 to the 12th power Gauss. Earth's magnetic field, for comparison, is about half a Gauss. An MRI machine produces roughly 1 to 3 Tesla, which is 10,000 to 30,000 Gauss. Take every MRI machine on Earth, combine their magnetic fields, concentrate them into a space the size of a city, and you'd still be short by a factor of roughly a billion. I've been sitting with this number for weeks and I still don't have an intuitive grasp of it. Some scales in the universe are genuinely beyond the reach of human imagination, and I think that's worth acknowledging rather than papering over with confident-sounding metaphors. At these magnetic field strengths, atomic structure itself behaves differently. Electrons don't orbit nuclei in standard spherical orbitals, they elongate along field lines into cigar-shaped configurations. Chemistry as we understand it, built on the geometry of electron clouds, essentially doesn't apply. Any object in the close vicinity of a neutron star isn't just being subjected to intense radiation, it's sitting in an environment where the fundamental rules of atomic physics have shifted. The pulsar wind compounds this. From the magnetic poles of a rotating neutron star, streams of relativistic particles, electrons and positrons moving at roughly 30% of the speed of light, continuously blast outward. Anything in proximity is being struck by these particles constantly. The X-ray luminosity from neutron stars ranges between 10 to the 31st and 10 to the 38th ergs per second. At the high end of that range, enough to sterilize any chemistry we know of across thousands of astronomical units. The object Webb detected sits at the outer edge of what's called the Roche limit for this system, the distance inside which tidal forces would overcome the object's own self-gravity and begin tearing it apart. Outer edge. It is, by the calculations, barely outside that threshold. If its orbit decays by approximately 15%, tidal disruption begins. So whatever this object is, it's not just surviving in a hostile environment, it's surviving at a margin that, by standard dynamics, shouldn't be stable. There are a few theoretical mechanisms that might explain how something could persist here. One is the radiation shadow hypothesis, a geometric argument that if the pulsar's beam precesses, wobbles slightly over time, the object might spend enough of its orbital period in a relative radiation shadow to reduce cumulative damage. This works only if the precession pattern matches specific parameters that haven't been confirmed. Another possibility invokes exotic matter. In 1984, physicist Edward Witten proposed the existence of strange quark matter, a phase of matter even denser than neutron star material, in which quarks exist in a free, deconfined state involving not just up and down quarks but also strange quarks. Witten's strange matter hypothesis, which has never been falsified, suggests this phase of matter would be thermodynamically stable and would interact very weakly with normal electromagnetic radiation. A body composed of strange matter would effectively be transparent to the radiation environment that would destroy conventional matter. This is a hypothesis, not a confirmed physical reality. But it's a hypothesis that sits within the range of known physics, not invented to explain this observation, but potentially applicable to it. The broader implication of an object surviving here carries its own weight. Roughly 30% of all stars in the Milky Way will eventually become neutron stars. If planetary remnants or second-generation bodies can survive these environments, if there's a second life possible for systems after stellar death, then our model of the galaxy as a place where stellar death is purely destructive needs revision. Death in this universe has a strange habit of leaving things behind. Now we come to the piece of data that was quietly tucked into the supplementary materials of the original observing report, the spectroscopic reading that one of the paper's co-authors wanted to re-examine before anyone else saw the result. Spectroscopy works on a beautifully simple principle. Every element, every molecule, absorbs and emits light at specific, characteristic wavelengths, a fingerprint written in light. Webb spectrographs can read those fingerprints with extraordinary precision, identifying not just which elements are present but which molecular bonds exist, which atoms are chemically connected to which. The resolution available to Webb in the infrared is something no previous space telescope could achieve for targets at this distance. The unexpected absorption feature appeared at approximately 3.2 microns. In spectroscopic terms, that wavelength corresponds to carbon-hydrogen bond stretching, the vibrational signature of CH bonds. Those bonds are the chemical foundation of organic molecules. Specifically, the feature is consistent with polycyclic aromatic hydrocarbons, complex carbon-based molecules that show up in interstellar molecular clouds, in meteorites, in cometary material. Finding PAH signatures in space is not itself shocking. They're one of the most common organic compound classes in the interstellar medium. Finding them concentrated in an object near a neutron star, however, raises a specific set of questions. The PAH signature was measured at 3.4 sigma above the background, which means statistically, there's approximately a 1 in 1,000 chance this is random noise. That's significant. But it's not the 5 sigma threshold the physics community requires to call something a confirmed detection. At 3.4 sigma, the right scientific response is neither "it's definitely there," nor "ignore it," it's "observe again." Which is exactly what the co-author requested. The second observation was conducted approximately 6 weeks after the first. The signal persisted. Same intensity. Same wavelength. Unchanged. Persistence rules out accretion artifact, a temporary accumulation of interstellar organic material onto the object's surface that would vary over time. A persistent, stable signature is structurally intrinsic. It means the organic chemistry is in or on the object itself, not a passing contamination. The alternative explanations for the signal are real and worth taking seriously. Certain metal oxide compounds can produce spectral features that mimic CH bond signatures in the 3.2 micron range. The accretion of carbon-rich ejecta from the progenitor star, material that was thrown outward in the supernova and then slowly gravitationally collected by the object over millions of years, is another viable source. These are the leading competing explanations among the team members who are more cautious about the organic interpretation. The reason the co-author wanted to re-verify before others saw the data, that specific human moment, the instinct to check again quietly before the community weighs in, is to me the most compelling beat in the entire story. Science is not a monolith. It's a collection of people with doubts and careers and competing interpretations, trying to be honest about the limits of what they can actually see. That caution, that desire to be sure, is what makes the result trustworthy even in its uncertainty. The paper has been submitted for peer review. The results are being evaluated. The community will weigh in. That process, slow and imperfect as it is working exactly as it should. But here's the larger question this data point forces. If this object isn't an isolated case, if there's a whole population of post-supernova bodies with exotic chemistry that we've simply never had the instruments to detect before, then our inventory of the universe is more incomplete than we thought. Consider the arithmetic. There are an estimated 100 million neutron stars in the Milky Way alone. If even 1% of them have detectable companion objects, bodies formed from fallback disks or surviving the initial explosion, that's 1 million potential objects we've never counted. 1 million worlds in a category that wasn't on our map. Webb's current observing program includes approximately 47 known pulsars being scanned for timing anomalies consistent with companion objects. Preliminary analysis, unpublished, unreviewed, has flagged 4 additional systems showing patterns similar to what the initial discovery showed. For potential matches out of 47 scanned, scale that to the full neutron star population and the implications become difficult to minimize. This reshapes more than just the planetary census. It reshapes the habitability question, the framework we use to ask where life could possibly exist. For decades, that framework has been built around one template: a sun-like star, a rocky planet at a comfortable distance, liquid water, a reasonable atmosphere. The habitable zone. It's a useful concept, but it was derived from one data point: birth. One star, one set of conditions, one type of chemistry. Every time we've challenged that template, deep-sea hydrothermal vents operating without sunlight, microorganisms in the Atacama Desert, life preserved in Antarctic permafrost, we've found that life was already there, operating in conditions we'd excluded from the habitable definition. Applying that track record to neutron star environments doesn't mean life exists there. It means we have no empirical basis for confidence that it doesn't. Extreme radiation environments, exotic chemistry, non-standard energy gradients, these are conditions that push against every model of life we've built. But those models were built around one example. There's also a consideration from SETI that deserves mention here. Neutron stars, because their pulsar beams sweep across space with lighthouse-like regularity, visible from any direction at virtually any distance, have been proposed as ideal anchor points for interstellar communication. Beacon locations. If a civilization wanted to place something at a position visible from across the galaxy, the vicinity of a known pulsar would be a logical choice. This isn't Avi Loeb's argument, it comes from Paul Davies in The Eerie Silence, published in 2010. The idea predates this discovery by over a decade. The discovery doesn't confirm it. But it adds a layer to the question of why something might be positioned exactly where Webb found it. The revision to Drake equation thinking follows from this. The original framework estimated, in the FL term, the fraction of planets where life develops, only planets around main sequence stars. Neutron star companions weren't a category that existed in the model. If exotic chemistry is possible in these environments, the input assumptions change, and the estimated number of potential sites for life in the galaxy rises. By how much is genuinely unknown. But the direction of revision is upward. What Webb represents in this context is a turning point instrument. Spitzer could detect fallback disks but couldn't analyze their composition in detail. Hubble couldn't reach the infrared wavelengths needed. Webb is the instrument that makes this category of discovery possible, and we are less than 3 years into a planned 20-year mission. What we found so far is a preview of a preview. Which brings us to the question I suspect brought many of you here. Not the science question. The other one. The Fermi Paradox asks, if the conditions for intelligent life are common in the universe, why haven't we encountered any evidence of it? The usual framing treats this as a numbers problem. If there are billions of potentially habitable planets and life arises on even a small fraction of them, where is everybody? The discovery we've been discussing makes the paradox sharper, not softer. If the definition of potentially habitable expands, if second-generation planets around neutron stars can host chemistry, if exotic environments allow for lifelike processes we haven't imagined, then there are more potential sites, not fewer. And the silence becomes harder to explain. One response to the Fermi paradox that this discovery makes more resonant is the great filter framing. The argument is that somewhere in the sequence from simple chemistry to spacefaring civilization, there's a filter, a stage that almost nothing gets through. The usual debate is whether that filter is behind us, something we've already survived, or ahead of us, something we haven't faced yet. This discovery introduces a specific candidate for a filter that hasn't been discussed as much: surviving your star's death. Most planets, most biospheres, most civilizations, if they develop, are tied to their home star. When that star ends, they end with it. The few that don't, the ones with the technology, the capability, the resources to persist independently, might represent a vanishingly small fraction of what emerged. We're currently at the stage where our civilization's existence depends entirely on one star continuing to function normally. That's not a comfortable position when viewed from this context. The cosmic timing angle deepens this further. Neutron stars that formed 10 billion years ago have had 10 billion years of potential second-generation planetary evolution. We've been anatomically modern humans for roughly 300,000 years. Whatever might have arisen near an ancient neutron star had a head start measured in billions of years. If it's still there in any form, evolved, transformed, or simply persisting, it would be unrecognizable to us as life or as technology by any standard we currently hold. And here's what I genuinely believe, and you're welcome to push back on this in the comments. The most significant scientific discovery of the next 50 years won't come from a planned experiment. It'll come from someone who refused to dismiss an anomaly. Wolzen didn't dismiss the weird timing signature. The Webb team didn't dismiss the acceleration data. The co-author didn't dismiss the spectroscopic reading. Scientific progress moves at the speed of, wait, that's strange. Right now, this is very strange. The honest scientific status at this moment is precise. We are not saying this is evidence of intelligence. We are saying, we cannot use ignorance as a default answer anymore. Webb has given us observational capacity we didn't have before. And the first object to demonstrate that capacity is something we don't fully understand. That's not alarming. It's an instruction to look harder, more carefully, and with more humility than we've typically brought to these questions. You are watching this at a moment when the data is current, the papers are in peer review, the second observation results are being analyzed. This isn't history. It's live. And your awareness of it, your willingness to sit with uncertainty rather than demand premature resolution, is part of the human response to the oldest question we ask. Before we close, let's separate clearly what we know from what we're still working out. This matters, because the story will continue to develop and you'll need a framework for evaluating what comes next. What is confirmed? James Webb detected timing anomalies in this pulsar system consistent with a companion object. The object's estimated mass is approximately 0.3 Earth masses. Its motion pattern doesn't match standard orbital predictions under gravitational dynamics alone. The spectroscopic data shows a possible organic signature at 3.4 sigma, significant, but below the confirmation threshold. The second observation confirmed signal persistence. What is not confirmed, the nature of the object, whether it's a survivor, a second-generation body, or something else. No non-gravitational propulsion has been established. No biological origin has been proposed in any peer-reviewed context. No technological origin has been established. These are hypotheses, some more supported by current data than others, all of them alive. The timeline for what comes next, peer review publication is expected, follow-up Webb observations are scheduled approximately 6 months from the time of this recording, coordination with the Fast Radio Telescope in China, the largest radio telescope on Earth, is active, and at least 3 independent research groups have announced plans to conduct their own analysis of the data when it becomes publicly available. How to follow this responsibly? When you see headlines, ask 2 questions. Is this peer-reviewed? Does the reporting separate data from interpretation? If the answer to either is no, hold your conclusion until someone does both. I want to be transparent about something. I spent 3 weeks on this video. I read the preprint 4 times. I changed my own conclusion twice. The first draft was more skeptical than the evidence warranted. The second was more credulous than the evidence warranted. This version tries to hold exactly the line between them, to say that this is genuinely uncertain and genuinely important at the same time, and that both of those things can be true simultaneously. I hope I found that balance. You'll tell me. We started this documentary with Webb locked onto a neutron star, detecting something that moves, something that has no clear reason to be there according to any model we had. We've now walked through the physics of what neutron stars are, the 3 competing theories for what this object might be, the environmental conditions that make its existence so difficult to explain, the spectroscopic data that quietly raised an additional question, and the broader implications for how we think about planets, habitability, and the population of the universe. The honest answer to, what is it? Remains, we don't fully know yet. But we know enough to say this: the discovery is real, the anomalies are real, the questions are legitimate, and the instruments we now have are capable of pursuing them in ways no previous generation of astronomers could. The darkest chapter in a star's life may not be the end of the story. And that matters, not just for whatever is orbiting that particular neutron star 6,500 light-years away, but for every world, every system, every star that has ever burned out in the dark somewhere in this galaxy. Death in this universe, it turns out, has a strange and persistent habit of leaving things behind. In approximately 6 months, Webb returns to this system with an upgraded observing protocol, deeper spectroscopy, longer baseline timing, coordinated with fast on the ground. Whatever they find, or don't find, will be significant either way. We'll cover those results here the moment they're available, because if a neutron star can have a companion that challenges everything we thought we knew about stellar graveyards, the follow-up data deserves at least as much of your time as this. And next time, we're leaving this system entirely and looking at something far closer, and in some ways, even stranger. There's an object at the edge of our own solar system, observed twice and never confirmed, that some researchers believe may be the reason our solar system is shaped the way it is. They call it Planet 9. And the new data coming from Webb is beginning to say something about it that the original theorists did not expect. If you've been following this channel, you already know that when Webb says something unexpected, it tends to be worth paying attention. We've spent 60 minutes in the dark together, orbiting a dead star, weighing evidence, sitting with uncertainty, and I'll be honest, if that object near PSRB 1257 plus 12 turns out to be a second-generation planet carrying organic chemistry at 3.4 sigma, the most unsettling part won't be the discovery itself. It'll be the fact that the universe had to kill a star to build it. Go think about that.